Hello, this presentation is titled Exploratory Data Analysis with Raku. It is based on a notebook I used to prepare an article titled Age at Creation for Programming Languages Stats. The data we're going to use is from the programming language database. I have taken it from this particular page of outside. So in this presentation, though, we're not that interested in the data and what this data tells us that much. We're going to, of course, discuss it, but we're mostly interested in proclaiming the Raku tools for doing exploratory data analysis. And these tools, they're in these four groups, right? So we have data ingestion, and the data ingestion needs to be relatively easy and simple. Facilitated data acquisition in general is a fairly complicated problem, but it needs to be facilitated at least to a point. Data wrangling and summarization, this is another branch of the tools, and we are going to see the use of the data reshapers, summarizers, the type system, and translators. So the translators were for visualizing the data, summarizers and type system were both summarizing the data. Data reshapers is mostly for transforming the data. There's some other packages in the Raku ecosystem, like say by Steve Rowe, for processing data. Very important part of data analysis is visualization and graphics. We're going to use the JavaScript D3 package. A very kind of rudimentary graphics package with text is provided by this text plot. The reason it's mentioned here is because text plot is actually provided by default with Jupyter Chatbook. So I'm using Raku Chatbook. This is a Visual Studio Code. It's with a Raku Chatbook kernel or the Jupyter kernel modification to facilitate large language models. We're not using large language models here, but I am using the Raku Chatbook nevertheless, right? You can do everything here I'm showing with the standard Jupyter kernel package of Raku, right? Okay, so here we do the setup. The more important part of the setup is that in order to plot graphics, the JavaScript graphics, we need to prime in a particular way this Visual Studio Code notebook, or same thing if you do it through the web browser. So this is an example plot. So this is how it looks like, right? So this the functions from the package JavaScript D3, right? This one, JavaScript D3. Those functions, they generate JavaScript code, and this JavaScript code is being executed in a browser. So Visual Studio Code being a headless browser, so we get this functionality. All right, so here I have done some additional setups for different colors used below. So the mind map above, I'm also having it here on this panel, and so we're going to be doing the data ingestion first. So this is with the data importers package, and it's this is here. It's the universal part I mentioned. So you can see here I'm giving a URL with a TSV file, and I'm ingesting it directly. So this is just one-liner. Data import can be used, but instead of data import, I have also overloaded the function slurp, and so we ingest the data here, and you can see with the deduce type we can actually sort of evaluate, see what we got. And so we have obtained a vector or an array of 213 elements. Each of these elements is a hash map or associative, and so we have this string to string hash map. So if I go here to this mind map, so with the data ingestion, I'm getting the TSV from the web, and then I have used this data type system to show some kind of structural summary of the data. Now I know what the data is. I mean, look, basically it's looks like this, right? We have the ID, the name, age of creation, and so forth, right? And so you can see here I'm using a certain order of the field names, which I'm going to use below. Then I'm converting the columns which can be interpreted as integers or numbers into integers. Again, I'm seeing the deduce type, and so here we can see a sample, right? Okay, of course, we need to see a summary of the data, and so we can see, let's say, tags, the last column tags. It has the most prominent tag is PL, which obviously stands for programming language. We have some other type of tags, but they're much less. All right, so here I'm picking focus languages: C++, Fortran, Java. These are just popular languages. Mathematica, Wolfram language. I'm going to be demonstrating some of this statistics also with Mathematica, just for comparison, briefly. We're mostly staying in Raku, so Raku is a focus language, same as SQL. And so here I have decided which are my top tags, and here I have made another column for the dataset, which is based on the focus languages and the top tags. All right, so one of the first things to do when we do exploratory data analysis, I mean, after the basic summary, is to do some sort of histogram statistics to kind of see distributions of the variables, right? So this is what we see here. And so fair enough, we can see, right, majority of the people have been creating languages between, say, 25, 20, 26, 7, up to 45, I would say, right? And you can see this with this box whiskers plot. It's like the interquartile distances. Same with the distributions for the appeared, when the language appeared, the year it has been proclaimed. These are years here on the x-axis, but they have been formatted as integers with thousands. Well, at this point, I'm not formatting axis ticks in this package JavaScript D3. So here the box whiskers plots, they can be used to kind of see, it's another way to see the distribution of the variables of interest, and we can see some tooltips with the summary statistics. So it's all in one place, right? Okay, so this is a digression here. In a presentation 2 years ago, I was discussing data wrangling and how it can be done with some minimalistic approach in Raku, and also how it can be facilitated using natural language processing or grammars or domain-specific languages which are being translated into code. So this is what you see here. This I can sort of demonstrate that this produces a certain data structure, and I'm going to visualize it, not visualize it, tabulate it here. So I have this function to pretty table, which visualizes what we have obtained. So what's happening here? I have said, well, use DS data, group by tags. This is the column tags, right? And then summarize the variable h at creation. And we basically summarized with several functions here, the number of elements, the minimum, maximum, and so forth, right? So if we find PL here, so PL here, 134, this is what we saw earlier. And then we can see the maximum is 70 years, the minimum is 18 years. All right, so this is actually not that important in a sense, right? This particular functionality, but since we're talking about exploratory data analysis, I'm trying to say that this has been facilitated in Raku, right? In order to access these functionalities, instead of knowing the packages, this can be done in a probably more intuitive manner in this way. All right, so the next thing we're going to be discussing is the Pareto principle manifestation. This again into the summary statistics. So we looked at the histograms and the box whisker plots, but Pareto statistics, they give you a very good orientation about the data. So what we can see here, I have basically, I mean, if you don't know what Pareto principle is, it's the 80-20 rule. And we can see it here, basically 30% of the creators or teams of creators correspond to 50% of the languages in this data set, right? So the statistic is it's computed by sorting the data in a reverse order and then normalizing. So this is what we see here. So in order to, it's very nice when you make this kind of Pareto plots to actually see what these points correspond to. I haven't implemented callouts in this package, but I have implemented tooltips. Here I'm going to show in Mathematica how the callouts are being done. So yeah, so you can see here, this is with callouts. So I actually started this project. I didn't want to be so involved. I wanted to do bubble charts like this, 2-dimensional and 3-dimensional. This was my motivation. So yeah, we are going to be concentrating on the bubble charts. But let me continue here with the Pareto principle statistics. So another thing to do is to look into the number of users estimate and imagine, which is not true, but imagine every programmer used only one language for life. They choose one language and stick for it for life. Then this type of Pareto principle plot would have been very telling. Of course, programmers use multiple languages. I'm not sure what is on average people do. I know that in data science, you have to know, say, at least, Python or R, and then of course you need to know SQL, and then you need to know Markdown. And so all of these languages I mentioned, Python, R, SQL, Markdown, are listed in this data set, probably Bash. So in a sense, from that perspective, obviously there's an overlap, but nevertheless, this plot gives us a fairly good orientation of what is the mind share of these languages. All right, our next thing to do is correlations. Again, we're staying in, we're still in this part of the plot. I have done some kind of minimal, sorry, I did not accentuate enough on this. There's a statistic, Pareto principle statistic, which is being computed. It's provided by this data summarizers package. So it is a summarizing statistic. All right, so we're staying into the graphics here. We're going to the pairwise correlation plots. Again, this is fundamental. If you have a bunch of numerical variables, you might be interested to see how they correlate. For example, what's happening here, we can see that the number of users estimate correlates with the number of jobs estimate. Yeah, sure. Now, what is happening here also is that in this particular set, I logarithmized the number of users and the number of jobs. They're pretty large and pretty distributed in such a way that if you don't logarithmize it, you get this meaningless correlation. In order to get meaningful correlation, you have to do the logarithms. What else I'm doing here is that if the two variables I wanna do a scatter plot for, if the two variables is basically the same variable, I'm actually showing a histogram. This is what you see here. So to explain this code here, I have taken certain column names, they're numerical, and I make a Cartesian product of them, and then for each Cartesian product, I'm visualizing a scatter plot. If we have the same variable, right, then we just show a histogram. So this is what you see here. Now I'm kind of cheating here. Here, and I'm going to demonstrate this. So I'm going to zoom out. So this is basically one big line of plots. It's not a table of plots. I haven't implemented this yet. To some extent, that's why I'm showing this messy code. I just haven't figured out what is a nice implementation of this pairwise functionalities, pairwise correlation plot functionalities. But something exists in Raku. It's actually pretty serviceable. If you want to see a proper implementation of this idea, it's here, right? So yeah, it's with a bigger awareness, right, of this tabular nature of the plots, and basically more or less the same plots are being seen. All right, so this is what I was saying, but if the two variables are the same, we're just going to see this kind of boring plot, which is a line, right, perfect correlation. So that's why in this particular case, in here, what I'm showing is actually a histogram. And we have seen the appeared and age of creation histograms, the others for the number of jobs estimate and the number of users, I kind of, you have this kind of very interesting distribution, right? There's a inverse correlation between the rank and the number of users estimate, which basically the higher the rank or the smaller the rank, the higher the number of users. Okay, makes sense. So yeah, let's move on. So the most important plot is the bubble chart, as I mentioned, and so you can see here these are the bubble charts, and they have been specified, these bubbles, to have tooltips. So you can see this is the language J. I think Kenneth Iverson is the primary inventor of J. At least I recognize that name. And he was age 70 when he did the language. So Raku by Larry Wall, he was 65 when Raku was released. So Mathematica and Wolfram language were here basically the focus languages, right? This with orange. So this is what I'm following. Raku is one of the focus languages. Mathematica and Wolfram language, they're basically the same language, right? Same inventor, but for whatever reasons they both appear into the database, and they appear with different type of popularity. Maybe people know them by different name. So this is the C++ language. This is Java. Somewhere here, it's an interesting question. Somewhere here should be Perl. Yeah, we see Perl here, right? Okay. So Larry Wall was 33, 34 when he released Perl. And so this is what we see on this plot. So what is happening here again, in order to make this bubble chart to be meaningful, I'm logarithmizing the number of users, and I'm kind of slightly cheating. I'm adding 1 in order the ones which are 0 to more or less be displayed. If you look at this plot, there's some minimum range which can be done which can be used for the bubbles, and so yeah, which lets us control how this plot looks like. The curator or the author of the dataset, break units, he told me to use foundation score, and maybe this is it's the time to mention where this discussion happened and how this notebook, the version of this notebook what I'm showing in the presentation, a version in Wolfram language with Mathematica, it was published here in the Wolfram community, so you can take it from there. The notebook which you see, it can be taken from GitHub, right? GitHub though does not give you visualization of the JavaScript graphics in the Jupyter notebooks. So so if you want to actually see the graphics, you need to open it in a browser. You need to open it in Visual Studio Code. So yeah, this is with the foundation score. I'm not going to dwell on this. So another statistic to do is the so-called second system effect. And so let's see, I'm not sure how instructive this is, but let's actually discuss what the second system effect is. So the second system effect, by definition, is something that some system which is successful, it's made a second version of it, and the first one was elegant and useful, the second one was cumbersome and too full of features, right? So the conjecture is that the more languages team of creators make, the less popular those languages are. So that's not necessarily because of the second system, right? It might be because all the languages, they have time to become popular and become useful. But I mean, I'm somewhat obnoxiously and kind of for fun name this phenomenon second system effect, or try to explain it with the second system effect. So here we're trying to verify that conjecture. Actually, the correct, that's a very strong statement. The correct statement is somewhat more relaxed, and it's here, given here. The most recent creation of a team of programming language creators is not the team's most popular creation. So this is what we're trying to kind of prove. This holds fairly often. So here, this is the, let me see, this should be, let me position this here. This should be Perl and Raku, right? Perl is here and this is Raku. So you can see, for example, for the Perl community, right? So the first language made by Larry Wall is Patch, then Perl, then Raku. So Does this actually hold? Well, I wouldn't say. I don't think it does. It holds in fair amount of cases, but it is interesting to make the statistics for this plot, right? So we basically group the data by the creators. We only pick those groups which have more than one language, and then we normalize by the maximum number of users for each of the groups. This is what is happening here, and then we do additional massaging, like say square root and whatnot. So probably this would have been better to be visualized in this way. Again, if I use this is not Raku, Raku is here, right? Raku, this is Pearl here, and this is Raku. This is probably better for visualization to kind of transpose the graphic. Unfortunately, we cannot see all of the inventors here, so that's why I use this bigger plot. Yeah, it's in my to-do list to figure out how to make this kind of long lists of groups, how to make them to be in several columns. All right, so going back here to this mind map, right? So I did show all of the elements here in this visualization branch. I would like to mention that the interactive reevaluation of the results, and continuous or like iterative massaging of the results and what we see with the plots and how we transform the data. That's very important. Having some notebook environment is very important. So here I'm going to go to Mathematica. Mathematica is the pioneer of notebooks. Jupyter was made or inspired from Mathematica. So you can see the bubble charts here are somewhat different. If we do the three-dimensional bubble charts, so you can see I have both callouts here and tooltips. Let me actually so the tooltips, yeah, so we should be able to see tooltips when we go here. So this is JavaScript, this is what Python, this is Java, and so forth, right? This is Raku, and so forth, right? So Mathematica is somewhere here. I think Perl, let's find Perl. I think it was very close to C++, right? So yeah, it's here. So this big red ball is C++, and this one here it's Perl. All right, so I have made also the balls, the bubbles somewhat transparent, and I did know that this is going to be a fairly interesting plot to make. This was my primary motivation to start doing this investigation. I didn't want to spend that much time on it, but well, I did. And one of the things we can claim, I'm going to finish with this, is that actually, yeah, Raku is pretty equipped to do exploratory data analysis. Thank you for your attention.